All right, so here we are in seventh hour, and then I'm going to shove these notes at you really fast. There's a lot of fill in the blank though, so it should be okay. And a lot of this terminology should be all right. So over time, all economies go through regular cycles of expansion and contraction. This is called the business cycle. Today we'll look at a graph depicting how gross domestic product, struggling here, changes with respect over time. So it's a roller coaster. It goes up, down, up, down. See it? Okay. Now I have these revealed for laziness on my part that the sentences are already created. But I'm glad I went through yesterday what I did because I don't know where else we were going to fit it. About increasing at an increasing rate, decreasing at a decreasing rate, the difference between a graph increasing and the rates of change increasing. Those are two completely separate concepts. You better have locked that in from yesterday. Those that were absent yesterday, unfortunately, I did not make a video. You better read those notes. Those are massively important to get on right now. All right, but anyway, maximum and minimum values of business cycle are called peaks and troughs. Label them on the graph. Okay, so these are the peaks and troughs, right? Hey, everyone. What are the slopes of the tangent lines that skip off these peaks and troughs? 3, 2, 1, say it. 0. So those have a 0 slope. I got to move this. I do expect old-fashioned group responses. I don't care if someone tells me that's wrong. I think it's great. What have I said if no one answers or if you don't answer? That's how I feel about you. That's what you are, right? You got to answer these questions so you're activated in the notes. All right, you got it, right? See that? Right. At point D, GDP is increasing. Yeah, D is on an increasing part of the graph. But here we go. Is the growth in GDP speeding up or slowing down? Let's see if you know the answer first, then I'll tell you why you should know it. Speeding up or slowing down, you have to choose one. 3, 2, 1, go. You are correct because we talked about yesterday. Why? What's the concavity? Down. That's what we did yesterday. That's what we got figured out. So it is increasing, but then the words would be at a decreasing rate. That was that one of those options, in the thing from yesterday. So that means it's slowing down, and why? Because the slopes of the tangent lines, I should have lines, decrease as you move left to right, and that's how we always move in graph land. Okay. So I did verbalize that. I know my chicken scratch is horrible. I apologize. At point E, is the average rate of change increasing or decreasing? It's really the same question. The rate of change, not the actual Y's. And what's the answer to that? 3, 2, 1, go. Ooh, this might be tough. I will say this. This is a point of inflection right here. So that's the point of inflection. So is it speeding up or is it increasing or decreasing? 3, 2, 1, go. Okay, I think decreasing. What's the concavity of E now that I put that point of inflection there? What's its concavity? So what is the rate of change doing? Increasing. I thought I heard a lot of decreasings, right? That's in a kind. So the Y's are decreasing, but the rates of change are going up as I move left to right. So this would be decreasing at an increasing rate. So that's what this is asking. What is the rate doing? Not the actual Y itself. So a lot of us missed that one, but that's okay. Hopefully we can get that figured out in the future. Hey, and then look at how I did the notes. Pretty weird, right? What does it say this is? Page what? Up at the top. 1. What's right next to it? Page what? 3, because turn it over. Page 2, I needed more space. All right? Now turn it back. We're on page 1. All right. Do put this. This is a discontinuity. This is actually called a jump discontinuity. Why? If you were a person running along this graph, what would you have to do to get to the next one? Say it. You'd have to jump. Whee! There used to be a game on your phones but it's old. You wouldn't know what it is, and I actually forgot what it's called. Huh? Who? Flappy Bird? I don't know. So I don't think that's what I was thinking of, but anyway. And then this is an infinite discontinuity. I think no, wait a minute. I don't think you've ever seen this before. Have I ever said the word asymptote? That sounds like a naughty word. Anyone? Asymptote? Have I ever said that in class? No. That's an asymptote. What an asymptote is a boundary that the graph cannot cross, but the graph behaves towards this. All right, and then that's what that graph is doing right there. There's actually another asymptote in this. We'll get to this later. This is a family of function thing, but I'm crossing you with my A-Bers. My A-Bers, we graphed that Tuesday, just the parent function for that. And then I swear, I hope I'm not thinking about AB, but I don't think I am. I swear to dog that we did you hear that? That's my phone. I can't look at that, right? I will. Okay. But I swear to dog that I actually did do order differences with you. But here's the problem. And even if I didn't, this will be brand new, and you may not have known what I was talking about, but I think I did with you guys, but then we didn't reference it again. And I think what we did was this, and then look at this. Use successive differences to find the degree of the polynomial. And I'm almost positive it was with you and not the regulars, but I may be wrong. Some of you did say that you didn't know about these differences when I was going through yesterday's sheet, like the chart of values and then first order differences and second. I think it was someone in here that said I don't remember that. So I could be wrong. But here's what we got to do. And this is, why is this -1? Sure, I went 49 minus 50, but this is what's happening as I have equal input values. Look at these. These go up by 1. So in this reading, you got to make sure you have common input intervals. So these go up by 1. What do the y's do? Oh no, 49 to 30. I was really bad the other hour, first hour, getting these numbers. Okay, so isn't that down 11, right? I was never good at math. It was always my hardest subject. What's the next one? -33, is that right? You guys agree? Someone could have a calculator. Anyone have a calculator? Okay. Nobody. I think this is -67, right? 5 to 0. What's wrong? What's wrong? Is there something wrong with that number? What's wrong? Why are we laughing at 67? There's something. I'm going to find out. I got this guy in this class, 7th hour. He's got some problems. The yip yapper. And then what's the last one? What's -62? I think I got it. Is that -113? Math was always so hard for me. All right, anyway. No one with this guy. All right. You know what this means? What this means is, first of all, the graph is not linear. I mean, come on, let's figure this out. If these were all the same, then those common differences in the y's would be called the what. What do we know about what a line has? The what? All lines are straight, okay? And that's like saying that there's a female girl. That's like a redundancy, all right? Don't say straight lines. That's something I can't stand. Anyway, what it starts with what? An S. Slope. That'd be slope. So it's not linear, but you know what we do know? The graph is decreasing. Come on. Of course it is. If these are all negative, then as I move left to right, they're going down. So this is definitely a decrease. Are you okay over there? It looks like you're rubbing your eyes already. Like this is too much for you. No, okay. All right. This is decreasing. Now let's do the second order differences. How far is it from -1 to -11? -10. -11 to -33. Isn't that -22? Yeah. And then -33 to -67. 34 down? Right? Is that correct? Because if we get these wrong, we're in trouble. And then -67, oh boy. 13, hold on, don't tell me. 70, carry the 1, 33, 43, 46. -46. Okay, I'll tell you what this means in a moment, but you know what? This is not quadratic. What you would need is second order differences to be equal, then the data would match a quadratic function perfectly. But it doesn't have common second order differences, so we're going to go a third level. Now this is down 12. This is down, hey, look at this, down 12 and down 12. So this means a cubic would match this perfectly in the future. Probably something you've done before is we would do a regression on this now, a cubic regression, and I would get a cubic of some nature that would fit this data perfectly, meaning that equation, these points would fit exactly on it. Now, this doesn't always happen in the real world. When we get into that regression, I'll talk about that in the future. But do you know what we do know in the second order differences? These are all negative, so therefore this graph would be concave down. So that's what the second order differences tell us. Even though a cubic may look like this, and I don't know which type of cubic it is. Remember the polynomial dance that we're going to do in October? This is a positive cubic. This is a negative cubic. But what I do know in this stretch right here of this order of points from 0 to 5, you would probably be on this portion of the graph. Because that portion is what? Concave, say it, down. So that's what I know. Now it could be like this. I don't know what kind of cubic going to fit this. It could have been that. It's either that or that. I don't know which way this cubic's going. We'd have to do a regression and see what it is. And I'll just leave it at that. There probably could be two different regressions. I don't know. I wonder what the computer would do with that. That's interesting, thinking about that out loud. And then you know what? I'm just going to shove these at you, and you do the best you can. You're now at 20, what does that say, 5? Yeah. I only have 20 minutes, and then the announcements and the phones, it's really like 18 minutes. So I got to go fast. Polynomial dance. This is yesterday's notes. So if I have even degree, I either have this graph where what did I get lazy about? Here, look at the odd degree, the limit statements. So what I'm saying is the limit statement for this would be limit of f of x as x approaches infinity, infinity. And then same thing for negative infinity. It would be both, because as I go, I guess I should write this on, I'm looking at this one. As I go this way for x's, this is what the y's would do. So that's what we're saying, that both limits would have that answer. But then if I have a negative even degree leading coefficient, then it's the polynomial dance down and down. So both of my limit statements would be negative. And I'm not, I got the limit statements written once. We've already talked about these. We've already yelled at you. We've already told you. I'll bring in Stranowski, the limit police, on writing your limits correctly. Oh, yeah. He loves, when limits are written right. Can't stand it when they're written wrong. It was crazy. All right, and then for odd degrees, I just switch. It'd be the exact opposite of these limits. And you should know how to do a limit statement. If you're missing limit statements, you are flushing points down the toilet. Look in the mirror, right? It's you and nobody else. All right, and then this next part, it's all cryptic and all written really weird. But we're going to talk about multiplicities of zeros. So this is a factor, and R1 is a 0. So x is our unknown, our input. All right, but then when you have raised to the mth power, then R1 has multiplicity m. And those multiplicities mean something for the graph. You did this at the end of last year. I hope. I don't think they changed this too much. I heard that they still kept this in. And R2, D2, has a multiplicity of n. Okay, so then what would happen if m or n was even? Then at that 0, we would have a bounce, which is the word tangent. We're going to, I think, put this all together tomorrow with some things going on there. And then if m is odd, I do need some differences. If it's only raised to the first power, then the 0, the behavior of the graph just goes straight through. Nothing special about it. It does look linear. Don't say straight linear. I don't like that. But then if the degree is 3, 5, 7, then it looks like a cubic when it passes through. It still passes through. You are going to have to do that. Now that looks like a heart. I don't have a heart. All right. What? All right. I do. It's just cold, black, and dead. Oh. Are you okay over here?
Yes.
These are my little jokes. Some people get all offended by these jokes, and then I end up in the principal's office. I don't get it. Kids these days, But you know why it looks like that? Y equals X. I say jokes in third hour, and they just look at me and drool. That's your sister. You tell her I said that. I don't know what's going on with third hour. Like I say a joke, and then one kid, his eyes, like he wants to murder me with his eyes. I don't know. I'm trying to do something to make it fun, and just like rabid dogs. You tell her. Okay. Anyway, I just found out that I teach a sister. I'm like, hey, wait a minute. That's what x to the third means. Got it? You can show her this video. I don't care. All right. Good. All right, so that's what an x to the third looks like. So that's why the 0 looks like a cubic there. Got it? All right, I don't know if I have time for this, all the screwing around. Let's get going. All right, and then this is a little weird, but it is true. We got to know what extrema are. Your third hour, they couldn't give me anything on the quizzes that we had. Oh, it was rough. All right, so extrema are turns in the graph, or they're actually high and low points. So relative extrema in this case, maximum and minimums. But look at this. This is a cubic, and I only have 2 extrema. You would always have 2 less, or down to. Now here's what I mean. I just graphed the cubic, and I graphed the y equals x cubed. So that's what that looks like. How many extrema do you see there? And the answer is none. The only thing that we have is a point of inflection that does change concavity. So we could have 2 extrema or less by 2, 0. Now let's look at an x to the fourth real quick. And I don't really have room for this, but here's a good x to the fourth. How many extrema do you see there? 3. It's degree 4, so I have 3. Or y equals x to the fourth, and that's it. I told you this. Y equals x to the fourth looks exactly like a parabola. It's just steeper, I guess. How many extrema does that have? Not 3, but 1. It's always 1 less than the degree or minus 2. So 3 or 1. So if I have an x to the fifth, I could have 4 extrema, or 2, or 0. And that's what I just had. I had 0 extrema with this x cubed. I could actually change this to y equals x to the fifth, and it's almost like the identical graph, except these would be steeper here. You still would have 0 extrema. So that's what you could have. You could have 4, or 2, or 0. All right? And that's how the extrema work. Points of inflection. Let's just look at a classic cubic. A cubic has 2 extrema, but only 1 inflection point. I hope that corner doesn't faint over there because someone just sucked a bunch of oxygen in with that huge yawn. Then he's looking around. Who did that? What? Anyway, all right, let's move on. Okay, now here's the tough part. You ain't gonna like this. But it's something you're going to have to do. And I'm not really a huge fan of this concept either, but even and odd. Because there's very rare functions that are even or odd. And it's one or the other. So here's what you got to know about even. Let me zoom in on what you should write. Even functions are symmetric to the y-axis. All the green that I have here is all the stuff that you have to do. And where are we at right now? 32. Oh my goodness. Stop screwing around, Mr. Samuels. Now, here's the reason why we have even, symmetric to the y-axis, y equals x squared. The word does come from even degrees in a polynomial, but that's not the only thing that's even. You're going to find out later that y equals cosine of x is an even function. And then, I'll just get it out of the way, y equals sine of x is an odd function. So I don't want you to think it's just even degrees. But here's what they have. They have symmetry to the y-axis. Look, here we go. 2 comma 4. You know that sound, right? That's a symmetry sound. We have symmetry with the y-axis there. But here is the mathematical test to prove even and odd. And we're going to do that on our next one. It's really the only math that we got going on in our notes today. And then here's odd. Sure, odd comes from this basic definition of a polynomial having odd degrees, but there's more. I just told you y equals sine of x is odd. You don't have to know that right now. Here we go. Sha-na-na-na-na-na-na-na-na-na-na. There you go. Across the origin, we have a reflected point, a reflected brother or sister, depending on how you feel about coordinates, that, are symmetric over the origin. Here is this test, and then I'm proving this test with this. Let me go back to this. 2 comma 4 and negative 2 comma 4 exist. That's what this says. When I plug in negative x for x, I still get the same output value. That's what that mathematical test means. But then look at this, 2 comma 8 and negative 2 comma negative 8. Oh, so when I plug in negative x for x, I get the opposite y value. See it? That's what this means. That's symmetry through the origin in this case. And I did do 2 cubed is 8 and negative 2 cubed is negative 8, and then showing the symmetry, that relationship holds true. So right there is going to be your algebra. But before I continue, if the graph is even, what would this new coordinate be? When I plug in negative x for x, I still get the same exact y value. That's the first test. I should have colored that in green. I don't have time to change colors. And then for it to be an odd function, I plug in negative x for x, and I get the opposites of y. And then you can see that 3 comma negative 18 is way down here. Negative 3 comma positive 18 is right over here. There it is, symmetry over the origin. Is everyone okay so far? I'll take that lack of response as a yes, and I'll move on. All right, so now let's determine if these functions are even, odd, or neither, and you don't have a graphing calculator. And plus, you can't really trust that graphing calculator. Here, say you're looking at the graphing calculator, and I'm going to ask you, is this even or odd? Which one is it? Wrong! Because here's the vertex. I did that on purpose. It's just a little bit off of the y-axis. You're gone. All right, and that's what I'm saying about you can't trust like the graphing calculator at all times. That may be a little bit off. So this doesn't have y-axis symmetry. It has a different symmetry, a different vertical line. This is why I'm not a huge fan of even and odd functions because they're very unique. There's barely anyone that's even or odd. But anyway, we're just going to go through it. So here's what we got to do. We actually got to do this test, and I'll color code this for each one just to make these look better. So I am literally going to plug in a negative x for x, and then I'm going to reevaluate this situation. Did I have this up here? I do. And you better follow the rules of PEMDAS in the next step. And that means this. Do I cancel these negatives that I'm pointing at? Yes or no? I have some people like this and some people like this, and you're gone. It's a no if you said yes. Sorry. All right? It's because you multiplied first before you did your exponent. Be careful. What's a negative squared? What's a negative to the fourth? So this is 5x to the fourth, and then this stays minus because I'm not supposed to cancel these, and then a negative squared is a positive. And you know what you got? The same as what you started with. So that means this is even because you ended up with the same thing you started with when you plugged in negative x for x. That is the even test for algebra. Even test for having an equation. Switching colors. So what happens when I do negative x for x here? What's a negative cubed, everybody? 3, 2, 1, go. And then you get lucky here if this was some other exponent. Yeah, you basically cancel those negatives because I have no power on that negative x. So a negative x cubed is a negative. And then now I can throw that negative out in front. And then a negative is a positive. And then I did do something funky where I pulled out a -1 to prove the opposite. But really all you have to see is this term is opposite this one, and this term is opposite this one. So this is odd because this was true. When I plugged in negative x for x, I ended up with the exact opposite function. Okay, I guess I will do that. In the other hour, I pulled out a negative out in front, and then I wrote this as 4x cubed minus x. So this is f of x, and then this is the opposite of it. So that's what that shows right there. So I did want to make sure you did see it the same way that they did. You don't have to do that last step. You just say it's odd. So you have to do these algebra tests. No choices. Oh boy. What time is it? Ah! Okay. So f of negative x. We got no time. Negative x to the sixth minus 2 times negative x squared. What do you think is going to happen? Even, odd, or neither? 3, 2, 1, go. Neither is right. One of these messes it up because that's the same. Nope, that doesn't cancel. Negative squared is a positive, so that's the same. Same. Oh, no. This is the one that jacks it up. That is the only term that turned opposite, and then the rest are the same. So this is neither. This is why I made page 2 larger. Okay? All right. Now, I do want to give you this one, and then this is going to build into tomorrow. All right? And then I don't think we're ready for imaginary solutions anyway. As we're at 39. What's the multiplicity on negative 3, 0? I did actually just cover this, so we should know. What's the multiplicity? 2 or? What would be another possibility? 4 or 6 or. We can do this how long? For forever. Thank you. That was the answer. All right, and then how about 2's multiplicity? 3, 2, 1, go. Oh no, 0. No, it is a 0. But what's its multiplicity? Sorry, 3. Or 5 or 7. How long can we do this? Forever. And then what about 4? For the first time in forever. Are you guys too old for that movie? Oh, Lexi loved that movie. Oh, I got to show you a video of her. Although she's a mean teenager now. Back when she was a sweet girl. Anyway, does the equation have any imaginary? Okay, fine. I'll cover it. What time is it? Okay. So if you cross this off and then had this part of the graph and this loop didn't hit the x-axis, that is the only way that you would know you have imaginary solutions as well. Come on, remember what that's related to. You did parabolas last year, and you had a parabola facing up that never crossed the x-axis. That's when you went to the quadratic formula and got I numbers for solutions. You need to remember that. Okay? And now the last ones, how do you find a y-intercept? You plug in 0 for x. I was going to do D, but I will show like example for all of these things. Sorry, there is a lot of stuff. And you actually, tomorrow we will specifically graph this, but keep this cryptic. What is the degree of this polynomial? We don't have time, so I'm going to give you a 3, 2, 1. 3, 2, 1, go. 6. And it would be a negative x to the 6th. So it is a degree 6 with a negative, so you would expect this behavior, like down and down. But you know more about zeros. We could actually make a sketch of this. I think we're doing that tomorrow. So what are my zeros? 0. Don't forget that one. -1 at multiplicity 3. That would go through like a cubic. We could make a sketch. We'll do it tomorrow. And then 2 has multiplicity 2 and it would bounce. So that's what you're supposed to do. Next one, as everyone's putting their stuff away. What are both of these limits going to end up being? Negative infinity, both ends. What was D? D was determine the y-intercept. How do I find y-intercept? Plug in 0 for x. Basically, you get 0, 0 on this one. All right, when you plug in 0 for x. E. Determine the possible number of turning points and possible number of inflections. X to the 6th, possible number of extreme is 5, inflection points is 4. Okay, that was that first page thing. Got it? And then the last thing, what's average rate of change? Find the slope. So input, say it. I would have to input -2 because it does say find the average rate of change from -2 to 1. So I have to put -2 comma and 1 comma and then find the slope of these 2 points. Isn't that easy? You know how to do that, right? Okay, we did it. You go get your phones.